Hi everyone, welcome back to our YouTube channel, Becoming a ROS Developer here at The Construct. My name is Rodrigo and today we have one of our students, Mohammad, who has completed the course ROS Basics in 5 days. And at the end of this course, you can present a project that is implemented on a real robot here at The Construct. So that is what we're going to be seeing here today. So hello Mohammad, how are you?
Hi, Rodrigo. Thanks, I'm perfect. How are you?
I
All
am
good?
good, thank you.
Okay.
I'm very excited to see your project. So whenever you want, please start sharing your screen and just explain to us how you've achieved this project, please.
Sure, yes, and I'm happy actually to today I'm here and present my project with you and others as well. So I'm going to share my screen. So if can you see my screen now?
Yes, I can see it.
Perfect. So this course is about the ROS, and we have mainly three sub projects that I'm going to explain. So we may first see like what type of projects do we have. So well, first we have this the very first project that I'm going to explain is about the wall following behavior that basically we have to follow certain steps that well, the general aim is that the wall following behavior is behavior that makes the robot follow along the wall on
Mm-hmm.
its right hand side, and which means that it should be moving forward at the 30 centimeter distance from the wall and having the wall on its right hand side. So we have to follow certain terms. For example, we have to subscribe to the laser topic of the robot, and also we have to publish the velocity topic of the robot, respecting these following terms. That, for example, the ray distance should, if it's bigger than 0.3 meter, we need to make the robot approach the wall a little by adding some rotational speed. And for example, if the ray distance is smaller than 0.2 meter, we need to move the robot away from the wall by adding rotational speed. And also, if the ray distance is between 0.2 meter or 0.3 meter, we need to keep the robot moving forward. And we also need to properly interpret the laser scan data, and we also need to test our code in the real robot. So let's see how we can implement all these tasks that we have here. So first of all,
Great.
here we have our robot. Yeah. So so first I start with the launching the code.
Mm-hmm.
So yeah. So here we have the list of our packages that we want to. Okay. So first of all, we start with the scan test, which has the basically the codes that we want for the first task. So first, before I move forward,
Mm-hmm.
I want to launch the well the just a moment. Yeah, the laser launch to see the range that this detects. Actually, this robot can detect, or the maximum value that it can detect actually. So so here we have this laser launch, and
Y-
well, as we can see that, so it shows that the maximum value that it can detect is 720. So
uh-huh.
the range is basically between 0 to 720. And so far what we know that well, the range is the range. We can move forward with the launching our main file. So and then I can move forward with explaining the code. Well, yep. So, so here we can see that our robot is start moving.
Mm-hmm.
And as we can see on the, if you can see the terminal, we can see that there are certain messages are, showing us that, for example, the wall is closed, move slow, or move faster. So basically, these comments we will see in the code in detail. But what does it mean, all these comments? So we basically are trying to see that when the robot is moving, respecting the terms that I explained in the beginning, for example, following the wall on its right-hand side, and also trying to avoid the collision with the wall next to it, or when it sees the wall in front of itself,
Mm-hmm.
and also the different obstacles that we have on the environment. So basically, the robot, the Turtlebot tree that we have here is, it has a LiDAR sensor, the LDS01, that we will see how exactly the details of this robot, or how this it can use this data, or the data that it receives from the sensor, to perform such behavior or move around. So yeah, I mean, here we can see that it's still, we have some messages here, but how it works. So I stopped the code to see maybe how the code works actually. So I here, yes. So for the first section, which is this scan test that I just explained, so yeah. So, well, first of all, we need to import some libraries, for example, the ROS library. And then we have to import the laser scan message from the sensor message packages to receive laser scan data. Then we need to have the twist message from the geometry message package to send the velocity comments. Also, we can have to see the list of available topics. We can have this ROS topic list to receive the list of available topics. And also with the echo, we can read information. For example, from the scan topic, since we need to know the certain values or certain parameters in order to define the variables. So in the following section, in the following lines, actually, I received this data from the scan topic. So here we define the variables. For example, well, first of all, the range, the sensor that I just mentioned, this LDS01 LiDAR, the range that it works is between 0.12 meters to and 3.5 meter. So the maximum range is actually is 3.5, and the minimum is 0.12. And then we define here other parameters that we receive from the scan topic, for example, the maximum angle and the minimum, and also the angle increment. Also, we identify here the speed actually here, which is a list of the minimum and the maximum speed. And then we start to defining our functions. So first of all, we have some functions here, some variables here. So which are the global variables, and are basically front readings, right reading, left, and the back readings. That well, the front reading is like the half of the length of the range that it detects,
Yeah.
or 360, the values in the range of 360. And the first quarter is for the right reading, or 180, and then we have the left reading, or the third quarter for the left reading, and for the back reading we have this 790 that we already see in the beginning, that the maximum value was 720 that we received. And then we call our function to decide the robot next move based on the sensor data. So then we define some functions in order to, actually give this ability to robot to move for different scenarios. For example, for moving forward, we set the forward speed and go 0 for, since it's moving forward, we don't need to have angular movement.
Mm-hmm.
The same for the backward movement, just by adding the negative value to actually to give this command to robot to move backward. And for turning clockwise and the counterclockwise movement, two functions for rotating to the left and to the right. And finally, another function for stopping the robot. So, and then we move forward with defining our last but not least function, which is the vol follow, which is also asked in the task. So we apply the criteria that I explained in the beginning.
Yeah.
That, for example, if we have no obstacles in the front, we, in order to see that the robot is properly worked, we add the print to see that, for example, the front is fine, so you can move fast. So we give this, you can move fast from the list that we have the slow and the fast speed. Then we have three criteria. So if the rate distance is between this 0.2 and 0.3, the robot needs to again move forward. So again, it should follow the wall and it should move straight by fast moving with using the fast moving. And also, if an obstacle at the right is further than 0.3, the robot must move closer to the wall. So we give it that you should move closer by calling this turn counter clockwise function. And if the obstacle at the right is closer than 0.2, the robot must move away. So we give a print function here that you should move further from the wall by giving this counterclockwise function. And then we have, if an obstacle is detected close in front of it, it should we add this print function that the wall is closed and you should move slow by giving this slow comment. And finally, for small detecting small obstacles on the way, if there's an obstacle less than 0.5, the robot must turn left until the obstacle at the right again is on the range of 0.2 and 0.3. So, and we add the print function here that it's too close, you should move reverse. And finally, we publish this velocity and the sleep for short duration as per the rate to limit the comment updates. And we have this main function that we basically initialize our ROS node. Then we publish to this velocity comment and we subscribe to the laser scan and we set the rate loop 20. And for example, it can be changed, but we keep it as 20 here, and we keep the program running until it's terminated. So basically, this was for the first task. But let's go through the second task, which is services. And what should we do for this section? Well, what is asked is that the goal in this section is to create a service server that when it calls, makes the robot search for the nearest wall. And for this, we have to create a service server that when it calls, it will make the robot to go to the nearest wall. And then we have to use the code that we had just I explained. And then we have to create a new launch file. So to launch the both nodes. So here we have the we have to create a service server. So we have this find wall service message structure that we have this request and response. So we can see that the response value is a Boolean value, which is the wall found, true or false. And then we have to follow this instruction or follow this criteria that when the service is called, the robot may perform the following behavior that first it should identify which laser is the shortest one, assuming that the one is pointing to the wall. Then it should rotate until it faces. Then it have to, the robot should move forward until the front raise is smaller than 30 centimeter. And then it has to rotate again until the ray number is 270. The laser range is pointing to the wall. And at this point, the robot is ready to start the following and it should return the true value. Then we have to test our service, and then we have to add the service call to the section 1 program and test our service and launch the both nodes at the same time. So let's see how all these things work. So I move a little bit the robot to put it in the proper start position, and then we can move forward. So, yep. So, yep. I mean, maybe somewhere here, maybe. maybe a little bit, yep, somewhere here. So maybe as a start point. So so we go to our code and see how we can do this section. So here we have our file here, which is for the wall follower for the service section, and we basically it here. Well, yep. I already explained the structure of our file. So basically, what we have for the our file here is structure of the file. So we can see the structure that here we have it. So and it's not one word here. So okay. So here we have the okay. So here we have this find wall message that we have the request and the response that it is a Boolean value that the purpose is to define a service message that returns a Boolean value indicating whether the wall was successfully located and aligned with by the robot or not. So here we have the structure of our message, and then we can run the code. We go to our launch file, and so sometimes I guess this code, if it's not hang, okay. So okay, we can see that the robot will start rotating until it should find the wall or face to the wall, and after that we basically expected that the robot follow the task one, which was the wall following. So in the terminal, well, here the robot's still rotating. After certain time, it should face its nearest wall. So
maybe it's too close to the wall. Maybe it's spinning too fast.
Yeah, I mean, sometimes yes, maybe it's well, actually I try to program it that is not rotating too fast, but maybe it takes a little bit time to find the wall, because actually the previous time I tried, it takes a little bit time, but maybe I can also change its position, maybe to move it a little bit close or far, and maybe see how it's.
Yeah, sorry to interrupt, Mohammed, but you have 5 minutes left.
Okay, so maybe I can try to move it a little bit closer, maybe. Okay. Yeah, so, and again, I tried, was launch. Yep. And detect the wall. I mean, basically, I tried several times. It works, but now I'm not sure that why it cannot face it in front of the wall. But
so
maybe is it? Maybe it's. I think maybe it's. It should detect, but I can move it a bit closer. Maybe if it cannot properly, or it takes time to detect the wall.
So hold on, can I interrupt here for a second?
Yeah. Sure, yeah.
Since we're running out of time, the one thing I want to ask is, if maybe the reason why it's not stopping. So how many values of the front did you consider when looking for the front of the wall, let's say?
Well, yeah, for the for this section, actually, for the values that I consider for the wall follower, this section. So, yep, here we have these values here. So, well, again, the values are for the here I define this post callback function that I same as the wall following behavior, that I identify this front, right, left, and back reading. And well, basically the robot should read these values from the range that is identified from
Yes.
well, to yeah. So that's why it should detect first. It detects the wall in front of itself, and then it start to move forward and
Right.
following
So you use that front value to stop and start going forward, right? And that's just only one value, right?
Yeah. Yeah, I mean, and well, this one, and also here
Is it though? I didn't catch that. Is it the one value that you're taking,
no, it's not. It's not the
or is
one
it a
value
range of
actually.
values?
Range of values, yes. There's the
Okay.
range of values that it can first detect the wall, and when it detects the wall, it can move forward. I mean, face to the wall, and then the rest will be the wall following behavior. But I mean, I can for the next exercise also, I can move for the
Yeah, can
next
we?
exercise.
Yes,
Odometry.
I'm sorry, Mohammed, to keep interrupting, but for the sake of brevity, could you just show us how you've achieved the action server? Because I have not seen that in action yet, and we
Oh,
do need to see
yeah.
it.
Okay, yeah. So, sure. Yeah. Well, I mean, the things that here we have is more or less the same as I explained in the previous code. But here we have this. Here we initialize the node actually, and we here we have this service client function to align the robots. Well, initially before starting the wall following behavior, and yep. So, and well, we have this ROS subscriber and follower, and we have this client. Sorry, I open this client. If it's open, I can show the code, but just a moment. I just want to show the code, but I'm not sure why it's not opening.
Huh.
Oh, it's okay, yeah. It just somehow it was just blocked. Yeah. Is it yes, client, and yep. So that's basically the structure of our, oh, yes, so here we have it. So here is the service client function that I defined. So we wait for the service that until the service is available, then we call the service proxy, which actually we create the service proxy, and then we have this find wall request. And finally, we call the service and wait for the response. And when it's completed and we receive the response, the robot will perform the task. So, well, yeah, I mean, that's basically for this section. And
Yes.
well, but there's a third part for actions actually that I want to also show that section, but I'm not sure whether that I have still the robot is not.
No, you have lost your reservation. It's been 26 minutes since we started.
26 minutes. So, okay, I mean, I can continue the explanation maybe on the simulation to see, to show that actually how it works. So, yeah, I mean, well, basically, the first thing I need to show on the simulation, the result actually. Well, yes. I mean, just a moment that I can show the simulation, and okay, yep. So well, we have more or less the same environment here, and well, for the second section, which is third section, which is the odometry that you want to receive the odometry list of the odometries that basically the robot is follow. So here I have the this odom recorder section that yep. So and oh, sorry, I typoed it. So, or maybe it's better that I place the robot in a better place here in the simulation, that we can also see that, yep, maybe start position, that we can see that when it's finished one loop, how it works. So, yep.
There are 2 more minutes.
Oh, yep. I mean, I just continuously it's showing like how it works. So here we have this robot that start moving, and at the same time also we can see that the robot is showing us every second that the distance is passed. So the robot is start moving forward and doing this wall following behavior, and meanwhile, oh, I think it's yeah. Oh, so where's the? I think I lost the simulation also, but the robot's still moving. Well, actually, yes, we can see that here that the robot is moving, and basically when it moves, it has to complete one lap, which is basically 6 meter. And when it's finished, that 6 meter, that unfortunately I mean the simulation now is seems to
It's
be
still
gone.
running, so I
But
don't
yeah, I
know
mean
why it
I
went away. Yeah, but
but what I want to show actually is that when the robot is completing, yep, when the robot is completing one lap, which I defined, which is like 6 meter for completing one lap. So it will show us that it give us a list of the odometries that the robot completed the task, and it shows us the
it
X,
should.
Y, and Z values. Actually, that I think now it should, when it's reached the 6 meter, it should uh, show the result.
The
So
list,
basically,
yes.
yeah, the wall following section is the same, but the only thing that I call the odometry section to show that the robot is and then we can see that, yep. So here, after finishing the task, it shows that the action is completed successfully with total distance of 6 meter. And also we have the record of the every second for the X, Y, and Z value. That this is for whole duration of the movement, which is basically the 6 meter actually. So yeah, I mean, this is for
Great.
the second section, but actually I'm not sure that I have time to explain the codes of
No,
this
we have
section,
ran
but
out of
yeah,
time now,
yeah.
unfortunately. So let me make some comments. First of all, thank you for taking the time to present. Uh, so yes, I have a couple of questions for you. First of all, congratulations. I liked the fact that you, for example, in the main node, control the speeds, and you have that fast speed, slow speed. That was real nice to see, and also really well documented. Really nice comments I saw. I didn't read all of them, but it's always nice to see. Helps you. And basically, I have 2 questions. Okay. So the first one is in terms of ROS, and I noticed that you ROS-cd into the package that you are trying to run something from, right? And then you do
Yep.
ROS launch
Yes, yes.
and the name of the launch file. Is there a
Yep.
reason why you do this?
Uh,
Is this a
it,
personal preference or something?
Yeah, actually, because I want to navigate, since I create for each one of these projects, 3 projects, I create a separate
Package.
package to run it separately and explain it. So that's why I use this ROS CD to navigate through the package that is, I mean, developed for the specific
I
task.
see.
So that's why I use this ROS CD to, I mean, properly go through the launch file that I'm looking, the package and the launch file that I'm looking for.
Okay, the reason I'm asking this is because you can actually, if you put that in the package and the manifest, package manifest and the CMake lists, you can actually, you don't have to do the raw
Oh yeah,
CD.
yeah,
You can just do ROS launch, name of the package, and then the launch file. That
yeah.
allows you to not have to navigate to where that launch file is and be able to launch it anywhere. So I was just curious. I mean, you can see that it works both ways, but I have a feeling that uh, just to recommend to stay with the convention because it can get confusing quickly.
Yeah, yeah,
And
yeah.
then my other comment in question before we run out of time here, but I still want to ask it is yes, we established with my question that the wall finder uh, is then spinning, looking for the closest wall. And
Yes,
you answered me that it's looking for a range of values.
yes.
My first question is how many? Because I couldn't see because the letters were too small. And the next question is how could you fix this so it doesn't spin indefinitely waiting for it to find the wall? How can you fix that?
Well, yeah, I mean, the for the first question, actually, the range that I identified is like that the robot, when it starts rotating, when the range is like 270, that it should detect that the wall is on this well, is on this right hand side. So it should face to the wall, and when it's face to the wall, it should well, approach to the wall based on the distance that it has. So, but when it's reached to the 30 centimeter, from the wall, it has to start to perform that wall following behavior and continue the movement. So that's the range that the robot basically should detect and performing the wall following
I'm
behavior.
sorry to interrupt. I think we're confusing things here.
Yeah.
So one is the index that you're talking about, the 720. Those are that is
Two,
the 270.
uh,
Sorry, that is the index of the right side of the robot, meaning it is the 270th index that it corresponds to the right of the robot. My question is, when you're looking, you're aligning the robot first, which didn't happen. You know, we saw it didn't happen. It was spinning. We were waiting for it to
yeah, yeah,
face the
yeah,
wall, stop, and start
yeah.
approaching it. My question
Yes.
is, first, that's not the 270th. That would be the 700 over 2. That would be the middle of the range, so it's facing the front. And my
Yeah.
question is it one index or is it a range of indices that
The
you
range, actually, the range that actually the list that, well, it detects the from, for example, the some of the values that are infinity, that are like it detects nothing, and some of the values that actually detects that, it shows us the value that it detects the wall, and it actually shows us that while it's rotating it detects something, which is the wall actually. And so then based on that we can decide, like the
my
robot can decide
my
to.
question is how many of these indices are you considering for that spin to stop? That is my question. How many
Oh yeah, I
indices?
mean, well, yeah, in the in the code that I developed for this section,
Yes,
if
let's look
I,
at your wall finder and you should
yeah,
have a front index
yeah, yeah,
or range of indices. That is my
yes,
question
yes,
and
yeah,
I'm not understanding.
yeah. So okay, so for this is well, for the client and for the, yep.
No, no,
So
oh yeah, yes, this is a finder. I'm sorry. Yes.
yeah, yeah. So Basically for this wall follow section, what I defined
Oh
here
no, I'm
is that
sorry, but I'm sorry again, but I'm asking about the wall finder. The wall finder. The
the
service
wall,
server that finds the wall, not the follower, but the service you called that
yeah,
made the robot spin. Where is
yeah,
I see, I
yeah,
see. Follow wine client. There we go. That
yeah.
is a
So
client to a server, right? On
yes,
line 23. I want to see that server.
yeah, okay. So yeah, and just because actually I also have the both the launch files for the both of them here. Firewall service server that yeah,
There we
sorry,
go. Yes.
I didn't see it, it was on the bottom. Uh yeah, just here I have this find wall function that here we have this function that by finding the lowest ray value, and this function search for the minimum distance from the laser scan data, so assuming the nearest point is the wall. So here I basically define this for loop actually that update the minimum if a new smaller value is found. And also I have another function here, which is align front, which basically this function will move the robot's front closer to the wall. And this function attempts to align the robot's front directly with the wall by rotating until the front sensor reading the match minimum
Exactly. This
detect
is my
distance.
question. We've
Yeah,
arrived to my question. My
yeah.
question is how many values of the LiDAR scan message are you using for the robot to stop spinning? How many?
Okay, the number of actually the number of I mean, if I correctly understand, from the range from I mean from the range from 0 to 720, I guess. If you
Yes, exactly. How many of those are you using for the robot to stop spinning and start going towards the wall?
okay, yeah, I mean, for that one, actually, what I define is like the half of the range, which is here as here I define this the
Half
main
of the
behavior,
range.
half of the range, yes. Here I define this function that which is the main behavior, and actually it defines that when the wall is found by the robot, it's moved closer, then it aligns its front array, which is 270, to the wall and return true if aligned this correctly. So basically, when it's find the wall, it's returned the true value, and it's start the wall following behavior.
Okay, so I think I'm thinking there's a barrier of understanding here, and my question was basically because half of the range is basically impossible, right? Because
Of
it would just stop right on the because that would mean the whole front half of the robot is
Yeah,
considered the front of the robot. So then that would mean that the robot would stop not when it's facing the wall, but when one of its sides is to a wall.
yeah.
And from what
So
I
the
see, and
first,
from what
I think the first
can I
quarter
finish
region, yeah,
this comment that I'm
yeah, yeah,
making here?
yeah, 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 yeah.
The comment that I'm trying to make here is that you're only taking one value from what I saw in your code. You're only inspecting one index. That was my question. So you
One
do
minute.
at the top of it, you extract things from your laser callback, and you do the length over 2, the length over 4 to get the front right side. That is one index. That means that based on the speed of the robot and the frequency at which your node is spinning, you are
Yeah,
gonna have trouble if you're using only one. That's why I always tell people, use 20. It's gonna be like a range of indices that you're checking instead of just the one point that is unlikely to be hit on a normal spin, and that's why we
yeah.
kept seeing it spin. That was my question mainly, but
I
unfortunately we are 12 minutes over time, so
yeah.
I'm thinking we're going to wrap it up here. So let me just go back here to my screen, and thank you very, very much for showing us your project. I recommend taking a look at how you can do that, how you can spin the robot and really understand the lidar versus movement, so we can avoid these things like the infinite spin, right? For the next time, maybe show the first time, the very first thing, the whole application, so we can see all the different components come into play on the real robot. But other than that, thank you for showing us your project. And to everyone else that is watching, I invite you to do the same thing here, to come and present your project and in order to get a certificate from us. So thank you again very, very much. And we'll see you guys next time in the next video. Bye-bye.
Bye.
All right.